This is a story about maps. Everybody has used maps. Maps have been around a long time. And there are many different kinds of maps. Take this map here on my desk, for example. This map is made out of leather. You can roll it up and put it in your pocket. And it shows a rather important part of the world. Here's the Straits of Gibraltar in Spain, and here you can see the Pyrenees, which separate Spain from France. This is a map of the Blue Ridge Parkway. The one thing this map doesn't show, though, are all the hills and valleys of southwestern Virginia and Tennessee. In other words, it's a flat map, and it's a little misleading because it doesn't show the terrain. There are other maps, though, that do. Here we have a picture of the Atlantic Ocean in 3 dimensions. In addition to the continents, we have a picture of the bottom of the sea and the mountains, the mountain range that goes down between the continents. When you stop to think about it, the 3-dimensional map has a lot of depth and additional information on it, and you can imagine how many hundreds of people, how many hundreds of years it took to get the information on that National Geographic map. We're going to show you some maps of magnets. I have a small magnet here. It's about 6 inches between the poles, which are the 2 ends. And the magnet is made of aluminum, nickel, and cobalt, called Al-Nico. And the pieces, the pole pieces on each end, are made of a special alloy of neodymium iron boron. This map can influence things at a distance because it has control of the space around it, even though you can't see it. Just as you can't see the ocean floor. Not only can we make the map in 3 dimensions, but we can also use the computer to color some of the points and to create color patterns of the fields around the magnet. This book I have here is entitled Gilbert, Galileo, and Harvey. Gilbert was probably the first man to put down on paper a study of magnet and magnetic materials. And he, for the first time, made it clear that the whole Earth is a magnet. Magnets come in all shapes and sizes, as you can see from the assortment here on the tray. Some of them are very small and made like cylinders. Some are bars, and some, like this motor magnet from the seat, adjust in your car. If I have a magnet and I want to test it, I can bring the probe up close to the magnet and see whether the blue end or the red end is attracted. Now this will show us something about the space around a magnet, but it doesn't allow us to make very good measurements. We have set up equipment that will allow us to measure the magnetic intensity very carefully over the entire area around different kinds of magnets. This is a simple magnet compared to some of the assemblies that we have used. The measuring involves some electronics and some design, and in devising these assemblies and measuring these assemblies, I've had the pleasure of working with two people I'd like you to meet. The first is Howard Johnson, and the second is Steve Davis. The three of us have been interested in learning more about magnets, and we are convinced that the first thing to do is to measure the magnetic fields. So I'd like you to meet Howard Johnson. Howard, it seems like only yesterday when we first met and you got me interested in these magnetic things, but I know you've been interested in them quite a lot longer. What started you on magnetics?
Well, I really got interested when I found out in a class in 1942 that a permanent magnet is created when you align the unpaired electron spins. Then I had a second thought that I thought was important, and that was that if we could get a hard enough magnetic material, we could keep those spins in alignment and use the magnetic fields that they produced.
Now, by hard, you mean not just difficult to put your finger on it, but it's a material that holds the magnetism very tenaciously. Is that right?
That's correct. It doesn't reverse easily, and it's almost impossible to magnetize unless you heat it up until you get thermal relaxation.
And these devices we have here are made of hard magnetic permanent magnets. Is that right?
That's right. We developed a gate, a magnetic gate here. And this gate is so built that we knock out one set of spins and use the other. So the whole face of this gate is composed of north faces. The front of this car here is also north, and yet whenever we put it here with a barrier, we can remove the barrier and these like fields will attract one another. So when we move the barrier, you can see that it is pulled through. Now we can take the car and reverse the fields. Now we have a south face, and here we have a north face. So normally that would attract, but you'll see here that it kicks the car back out.
It goes just the other direction, doesn't it?
Yes. We can use the double spin theory and other applications, and we have one where we have the vortexes or vortices on their sides, one right after the other, and we'll show you this here.
Now here the magnets are underneath.
Yes.
And there's no gate as we had over there.
That's right. Now we have a unit here, as I mentioned, where we utilize multiple spins. But you can see that even though we have this loaded some with lead, it still runs all right. We're just separating out the spins and using them. Now we have a heavy duty unit over here that we'll take a further look at. Now this is a transition where we have the same kind of principles that we were using over there. It's only a more heavy duty unit. We will use a lead block before we get through here that brings the weight up to 35 pounds. Starting from a dead standstill. this is the first patent that was granted. We received 28 claims, which was all we asked for, but it took a long fight in the patent office and going before the Court of Appeals to secure those. Mapping the elusive magnetic code is not too easy, but we believe it is just as important and as basic as the double helix is in the genetic code. The double vortexes enable us to see and understand how attraction and repulsion works. It shows us how magnetic fields interact, and it shows us how that amplifying effects can be gained. It's a very definitive way of looking at magnetism and should be highly useful in finding out what we can do under circumstances before we go to all the expense of building everything up.
Now I'd like you to meet another member of our magnetic mapping team. He's a young electrical engineer, graduate of Tech, by the name of Steve Davis. Hi, Steve.
Hi, Dr. Bauer.
We're going to try and show you some of the equipment that we use for mapping the fields around magnets. Steve, what is all this paraphernalia that you have here?
Well, this is the system that we use to map the magnetic fields. When we first sat down and talked about mapping these fields, we began to realize that we just had much more data than we could take by hand, by moving the probe around by hand. So the idea was to develop a piece of hardware which would automatically position the magnetic probe within the magnetic field, and then to develop a software which would acquire the data from the probe and store it on the computer in a form that we could look at and analyze later. This gives us the advantage that everything is done very regularly, very precisely, so if we need to, we can go back and retake the data, rerun interesting plots, and try to come up and verify runs that we have made in the past. When we decide to map a magnetic field, we will take a magnetic structure, this being an example, and position it within the active area of the plotter. At that point, the computer will move the probe both in the Y direction and in the X direction, and for each position where it decides to take a measurement, it will stop the probe and then measure the field strength at that value.
The linear amplifier then will take the signal that the probe sees and send it to the computer, and there it will be digitized and recorded.
Right, exactly.
Well, let's look at some of these patterns on the computer. Well, this is the computer we've been using, Steve. Let's see what we can bring up on the screen. It might be interesting. What do we do now that we're over here at the computer and we have recorded the signals on a disk as numbers? What do we do next?
Well, we can look at this data in a couple of different formats. The first thing we normally look at is just to get a surface plot of the data to see what it looks like, what the actual field looks like under the probe.
Can we do that for that magnet that we looked at earlier?
Sure. We load up the program, and the first thing the program asks us is the name of the data file, and so we'll just enter the run number of that data file and modify a few parameters here for the program. And now it will load the information in. It's loading it in off the hard disk, and as soon as all of the information is loaded, it will produce a surface contour plot. Since we normally acquire data in a very regular format, in actually a square format, you see those squares on the screen here.
I see. So each one of those represents a point.
Right.
So
And there will be thousands of data points in each data run.
Now, what do you do with this? Do you build some sort of a diagram out of it?
Sometimes, if it's particularly interesting field pattern, we will actually build a physical model of it. This, for example, is a model that we built of one field that we mapped.
And it's strong here, and it's strong here, and then it fades away in the opposite direction at these 2 points. Is that right?
That's correct.
Now, what else can we do with the data that we have stored on this disk here?
Well, sometimes we're interested in the orientation of the magnetic field strength vectors. And so we have another program which plots the orientation of those vectors in colors, which enables us to determine whether the magnetic field is north or south at a particular orientation, at a particular physical location. For this example, we will plot the first orientation, and we will just show each vector location as a dot on the screen.
Now, suppose we go back to the menu, and we change the order, and we connect the dots. This is the same data now displayed in another way, and showing the areas or the regions where the field is positive or negative, depending on whether the color is green or red. And now the origin is moved over here, but it's the same data. Mm-hmm. That gives us a chance to look at magnetic assemblies in a somewhat different way. Mm. Well, there you have it, a sort of a vignette of how we go about mapping magnetic fields. You can see we use some fancy equipment and some not so fancy equipment. And I hope we have been able to communicate to you the fact that we enjoy what we're doing. And we are doing something that is quite interesting and maybe someday will be of use to somebody. Howard, you have quite a few of these fields now.
Yes, we do, by courtesy of Steve and his equipment building and recording devices, as well as the programs that enable us to see many things that have not been seen before.
Well, I hope you will agree that some of the things we are doing are interesting, and that perhaps not everything has been discovered, that perhaps not everything is known about magnetic fields, and that as we learn more about them, we may be able to put them to some interesting uses.